Hello folks, we're back with another episode of Multivariable Calculus. Today we're going to go into double integrals. Before we start double integrals, I would like to go and review single integrals, okay? The normal integrals that we've been doing in Calc 1, because we're going to quickly do the same stuff for double integrals. It's going to be much faster if we review our old stuff. So the idea here is when we had a function of two variables, we have the x-axis, we have the y-axis, okay? And let's say we have a function f of something of this sort, okay? So let's say it's between a and b. This is the x-axis, and the function is f of x. Now, if I wanted to do the single variable, define the single variable, the trick that we did was basically we divided this up into many rectangles, okay, something like this, and then maybe we took the right hand points, and instead of calculating the area under the function, we calculated the heights of these, the areas of these rectangles, okay? So maybe something like that, something like that, and something like this, and this one's going to be like this. Okay, so we have some error. Okay, it doesn't exactly fit the curve. We have some error, but the idea was if we let the limit of integrals be if we let the number of rectangles be very large. In other words, as the number of rectangles goes to infinity, we could pretty much say it's exactly the same. The areas of the rectangles, when we sum up, we get the area on the under the curve. So the trick that we did, remember, was we let a be equal to x sub 0. So this is x sub 0, this is x sub 1, x sub 2, and so on. Okay, and that's less than x sub 1. And we divide, let's say, into n pieces, and the nth piece is b. Okay, what we did was you could take your height to be on the function any point. Okay, so I did endpoints on these ones. You can take, okay, so maybe here. All right, this one's good. So you could take your height to be any point. Let's call this x sub I. Let's call this x sub I minus 1. Any point between here, x sub I minus 1 and x sub I. And you could draw your rectangle. So the area of I rectangle would be, right, x sub I, the right hand point, minus x sub I minus 1, okay, times, okay, I would have to multiply this by the height of the function, and let's call that point c sub I, okay, and that would be the area of the rectangle. So here c sub I is this point anywhere between x sub I and x I minus 1. It doesn't really matter. Okay, so the idea is we want to add these up. We want to add these up to get the area. So my area approximation would be roughly I equals 1 all the way up to n. So I have n rectangles, and the area of each one of them was f of c sub I times x sub I minus x sub I minus 1. Now, of course, this looks like, this looks like an alien language, so we made it easier on ourselves. We said this was going to be defined as delta x sub I. So when I say delta x sub I, it's the change, it's the length of the ith interval. So we could write it nicer. It looks a little bit nicer, not too much, but a little. So you could write it like this, delta x sub I. Okay, so the idea here is that we would expect, if the limit exists, of course, this to be limit is n goes to infinity of these, of these guys, right? So if I do it with infinitely many rectangles, I would get exactly the area under the curve, okay? Now, instead of limit as n goes to infinity, you could replace this by the norm of the partition goes to 0. So this is a funky term. This is more generalized. This was Riemann's idea. So this is the Riemann integral, as opposed to there are some other integrals like Lebesgue integral. This was Riemann's idea, was that the intervals here don't have to be all the same length, okay? So some of them could be a little fat, like I drew here. Some of them could be tinier, okay? It doesn't matter how big or how small the integrals are, as long as the length of the largest one, the base length of the largest one goes to 0, you're going to be fine. So for all intents and purposes, we usually divide into equal intervals so that they'll be easier for us. And then we calculate the Riemann integral like that. So if you remember, this was kind of a pain, right? Calculating integrals like this. And the reason we learned this was because um, there's a fundamental theorem of calculus which says, okay, you do the integrals by taking antiderivatives, but there were a lot of functions out there that did not have nice antiderivatives, right? It'd be very hard to calculate the antiderivatives of, like, e to the minus x squared doesn't have a nice antiderivative. So sometimes all you can do is these approximations, okay? And a computer doesn't get tired. The computer, you can tell the computer, hey, divide into 10,000 pieces and take the heights, appropriate heights, and calculate the areas of the rectangles, and that'll be roughly the area of the curve. Okay, so why did we do all of this? Why we were supposedly supposed to do the double integrals? Well, we reviewed our single integrals because we're going to do the exact same thing for double integrals. Notice that the idea of integration was motivated by our need to find the areas under curves. So now we take it one more step up. In 3 dimensions, if we go on to 3 dimensions, we will be needing to find volumes under 3-dimensional surfaces, okay? So you can generalize the idea to 4 dimensions, 5 dimensions, whatever, but this 3-dimensional idea is very nice. So I have some kind of slide here, okay? So it looks like something kids could slide on, and I'm wondering what kind of volume it has, okay? So to keep the problem simple, I'm going to assume that the slide is set up just like a kid's slide over some rectangular area R, okay? So if I looked at the shadow of the slide, it would be rectangular, okay? And the slide is defined by the function z equals f of x, y. Okay, so I drew these before I started. Usually I draw with you guys because my drawing capabilities are horrible, it's very hard for me to draw 3-dimensional shapes. You can see it's not very pretty, so I didn't want to do it on the fly. I'd rather do it beforehand, so at least you could see some ideas. Now, usually the books have very nice drawings of these, so I would suggest you go and check out your favorite calculus book. But the idea is we have a three-dimensional surface, just a kid's slide, okay, and we're wondering what kind of volume is captured under it, okay? Maybe you want to put the spaces empty, maybe you want to put your stuff in it, the old boxes or something like that, okay? And I drew the x, y, z. X is going this direction, y is going this direction, z is going up as usual, okay? So the slide is going to be over the rectangular box. The x coordinates are going to range from a to b, and the y coordinates are going to range from c to d. So I said the region is a comma b times c comma d, so that's a rectangular region. Okay, so now what are we going to do? The first thing is I'm going to draw the region so that we're looking top down now. We have this region, and this time I'm going to break it into lots of small rectangles, okay? So this is the whole region, and I'm going to break it into lots of small rectangles. What I'm going to do is I'm going to look in the x direction, and I'm going to break it into m pieces, and I'm going to look at the y direction, and I'm going to break it into n pieces. So I'll let this number, whatever, so how many rectangles are there? There are m times n, okay? And I'll let that number be equal to k. I don't want to keep writing it over, and I'm going to concentrate on the ith rectangle, okay? So this little piece here that I've shaded, okay? So the idea goes is that we're going to pick a height of the function inside this interval. So by what I mean is that we're going to pick a point, maybe right here, this fat point, okay, that I'm doing right there, okay. Wish we had a different color pen. Let's call that x sub y sub I, x sub I, y sub I, and the only property is you can pick it as low. You can pick whatever point you would like. You would like as long as it's in the ith rectangle. Okay. So here is our setup. This point A is equal to x sub 0. We're going all the way to this point B. That's equal to x. That's x sub m. And here, actually, let me write those. Here is A is equal to x sub 0. This is x sub 1, x sub 2, and so on. And this is x sub m, and that's B. Okay. On the other side, that was the x. Now, in the B coordinates, C is equal to y sub 0. This is y sub 1. And all the way up to D, which is going to be equal to y sub n. Okay, so it's m times n. So that's exactly what I wrote. And we're going to say is that calculating this area is very easy. It's a rectangle. So whatever it is, we're going to let A sub I be the area of the ith rectangle R sub I. Okay. So what we're trying to do is we're looking at the height of the function exactly at that point, x sub I star, y sub I star. Oh, sorry, these guys were supposed to be stars. Okay, x sub I star, y sub I star. And what I mean is, so we took this point maybe here, and I looked at the height of the function. So now instead of a rectangle, I'll have a vertical box, right? I have a vertical box. So if I take the heights of the vertical boxes to be the height of the function, and I do it over all of these rectangles, I should get something pretty close to the volume, okay? Just like the single variable idea. So the volume is going to be approximately, I do this for all the boxes, from the first box to the kth box. Remember, k was equal to m times n. And what I do is to calculate the volume, well, I need to find the area of the box, well, area of the rectangle on the bottom, which was a sub I, times the height of the box, and that was z sub I. What was it? That was f of x sub y star, y sub I star. Okay? Now, one would expect that then the volume would be, we would get exactly the volume, not the approximation, but exactly the volume when limit as k goes to infinity. I did from the first rectangle to the kth rectangle, and I calculate the volumes of all those boxes and add them up. Okay? So if the limit exists, we're going to call this the integral of the function over the region R. Okay? The integral of the function over the region R. Here, this dA corresponds to this delta A. So this is the infinitesimal area. Okay? Infinitesimal area. So that I would expect it to give me the volume if, of course, there's a big if here, if the limit exists. Now, the limit might not exist all the time. Okay, it might be bad. But if you have a continuous function over a closed rectangle's closed, okay, it will always exist. Now, just like single variable, we can be a little bit more sophisticated. So the way I drew it was all the pieces were equal up here, right? All the pieces, so I divided equal to m equal pieces, and then I divided the height into n equal pieces. Well, the pieces don't have to be equal. What we'd like to say is, as long as the largest rectangle, the area of the largest rectangle is finite, we're good. Then as the area of the largest rectangle goes to 0, you must get infinitely many rectangles, right? But that's the same thing as the area of rectangle is going to be finite if the diagonal is going to be finite, right? So here, the norm of P, the norm of the partition, we'd like to go to 0, where the norm of the partition is the diagonal of these largest diagonal, or you might want to say the area of the largest rectangle is the same thing, okay? So this is the definition. This is kind of the Riemann definition of calculating volumes. Of course, us being engineers, right? I mean, I'm a mathematician, but I'm sure we have a lot of engineer friends out there watching it. Nobody likes to do this stuff, okay? So we might have to do this when the function is not nice. It doesn't have a nice antiderivative, but we'd like to be able to do this in terms of antiderivatives when the antiderivatives are nice. So that's going to be in our next episode, and I'll see you then. Bye-bye.